Yeah. This is a little theoretical, kind of abstract thing. If you've ever instantiated an object, I think the first lady up there said you guys mostly look at Ruby here. This is in Python. You instantiate objects, and then somehow, magically, the compiler or the interpreter releases them, returns them to the operating system after you're done with them. How does it know how to do that? Well, the technique is by itself pretty simple, but there's a small catch. The way it works is every object has an extra field, which is just an integer called a reference count, which is incremented every time an object is, or a reference is added to it from another object, and then decremented every time a reference is removed, which is fine. When it gets to 0, then there's nothing referring to it, and you just call free on it, if you've ever used the malloc and free APIs in the C library. But there's a catch. Say we've got a reference over here, which is an object referring to another one. We've got a list over here, which is referring to a lot of different objects. But then, if two objects refer to each other, it's a big problem, because when no other objects, the entire rest of the program is not referring to either of the objects anymore. They'll still be referring to each other. The last time you removed a reference to one of them, the reference count went down from 2 to 1, and now they're both at 1. Neither one of them went to 0, and you'll never find them. They'll be stuck there forever. You have a memory leak, even though you're using, this advanced technique of counting. So what you have down here is, your basic reference cycle. These are program variables. They're pointing to or referring to these objects in memory space. If you remove this object, then this reference, and this object's reference count goes to 0. But it's not the case with these other ones, and we're going to talk about how to fix that. With me so far? In C and C++ and compiled languages, variables and objects have a closer relationship than Python, and I presume Ruby. I don't know for sure. Say these are the variables A, B, and C in the Python interpreter, and they're pointing to objects. The actual variable itself is just a pointer, no matter what goes there, whereas in C, the variable itself could actually be a more complicated structure, which is kind of interesting, but kind of a tangent too. So A is pointing to just a single object that's normal, but B and C are pointing to this big mess over here. If you remove any one of these, not any one, if you remove this one, then we can free this one. This one will go to 0, but these three will still be alive. If you remove this one, everything will still be alive. And if you remove this one, if you remove this one, this will still be alive. If you remove this one, all of them will still be alive, same thing. So what we're going to do is treat these objects like a graph. Have you guys ever looked at graph theory, graph algorithms, breadth first search, depth first search? Have you ever used mark and sweep or written one? Basically, yes and no. You go through all the objects that you want to look at, treat them as vertices in the graph, and set a mark flag, or just a single bit somewhere in the structure. You set it to clear before it's visited, or initialized to 0, and then set it to 1 once you have visited it. So that way you can go through and, from one object, go to or visit the neighboring objects, and use that mark bit so that you don't repeat yourself and enter an infinite loop, visiting the same objects over and over. Do we need the diagram for that? Might be helpful? No. I didn't have one. I'd have to draw it. Do you want to turn the lights on? See if you can see it from back there. Can we put up a blank screen or something, or just leave this off? Perhaps, possibly.
Just open a new tab, like in your browser. It'll be blank.
This isn't mine. Brian, how do you do that?
Control T. Or not.
Just blank?
You done with it? Just close it. You done with it?
Yeah. We can open it back up later.
There we go.
Does that have a backside?
Yeah, there's something on it.
Oh, okay. Feel free to erase what's on the front.
Yeah?
If they don't have it by now, they don't really need it.
Anyone have the Wi-Fi password?
Did you see the magnet here?
No.
That's really cool. Start with an example of a grid. Say you're filling pixels in a bitmap or something. I don't know if anyone's ever tried to write a paint program. I've tried at least once. You start here, and you try to fill everything. So you go to this one, and from here you go to this one, you go to this one, you go to this one, you go to this one. How do you know not to go back here?
Because you marked it.
Right. Yeah, because you marked it. That's true, but then you might not fill the same point, or then you might not fill the entire region, or if you're filling it the same color that you start at, then you might not fill anything.
There you go. Yeah. Why you're tracking separately.
Right. I think you need an extra monochrome bitmap
Yeah.
for that, and you have to fill that first, but you get the point. Cross your fingers.
Password.
Hey, Brian. Good. Yeah, we opened the new tab. That's where it was. We meaning me, sorry. All right. So, but if we removed one of the references, we're still okay. But if we remove two of them, we might have some problems. Say you remove this one and this one, you'll be able to free this one, but your cycle will be left over. Or say you free this one and this one, you'll be able to free this one. The reference count will go to 0, but these two will still have counts of 1. So we're going to do the mark and sweep thing and try to figure out if there's a cycle somewhere. Easily said, easier than done. The add reference implementation is pretty easy. You won't be able to use this code exactly. You can import it, but what? Bigger? F11? Do you want a bigger? One said make it bigger. Go. Dinner. Thank you. In your actual implementation, refs out would be some kind of structure. You'd have to iterate over your references. Say you have one field that's referring to employee name, another field that's referring to employee address. You'd have to iterate over those and replace the refs out with that. But for the example, which is why you can't actually use this code, we're just using a list. So add reference is append the reference from A to B to the list of references in A, increment the reference count in B, and you're done. The problem comes in when you start to remove the references. It's when you might get the memory leak. Do you want to read some of the module document where it says how to do it, and then look back at the code, or just look at the code? Yes, no? All in favor?
Look at the code.
Figures. All right. So, this is our fake list of references here. Again, there have to be an iteration. The way the Python implementation does it is it uses the visitor design pattern. It calls visit on A, which calls a function that the type of A has to implement, which iterates over all the different fields, calling the visit method on each one of those, and that calls back into one of the functions here, for example. But just for the discussion, we're just removing it from the list, and this doesn't take the right amount of running time, but again, still just an example. You decrement the reference count. That still works, and you still do that no matter what in every case. This is a convenience alias, or more accurately, an inconvenience alias. Excuse me. We get a couple of early exits that are possible in this algorithm. Normally, it's pretty slow, but sometimes there's exceptions where it won't take, or won't run as slow. If there's a second occurrence of B and A, say employee name and employee first name, point to the same string, then you can return early, and we'll have to call this function again when we get to the second occurrence of it. That's a possible early exit, but otherwise we're going down to stage 1. And if anyone looked at the link that I put, if it made it on the mailing list or on the website anywhere, I think there's 4 stages. Let's see. Whoa. Stage 2, stage 3, stage 4. Yeah, 4 stages. And this is before stage 1. Starting stage 1, we're going to do a depth first search, which is the kind I was looking at over on the whiteboard. We're going to add the guts of the search is adding to the end of the queue, which doesn't occur, which you don't find out till you get to the middle of it, which is not a very good, not a very easy, piece of code to present. But you find out eventually. You can cheat and look ahead. You start off with B, the object that we're removing the reference to, and then we're going to keep going so long as we have any left. We're going to take something off the front of the deck. No, take it off the back of the deck, excuse me. Taking it off the front would give you a breadth first search, and we'd have to use the pop left method. Then we're going to iterate over all the references that that object has, which in the first case is going to be B, but in the next case is going to be something that B referred to, which might eventually get us to the to our cycle. If we haven't visited yet, the initialization requirements are that count has to be 0. If we haven't visited yet, then we can append the thing that B was pointing to. Sorry, what? Yeah. Otherwise, we increment the reference count, and that's it. So when we're done, we have the count field of all the descendants of B, filled with the number of other objects that are referring to that object. Did I say that right? Sort of. Read the documentation. You want to do a diagram of that? Why not?
Sure, yes.
Oh wait, we'll need the password again. That's not convenient. Can everyone see off to the side here?
Just make it like text file. Oh, yeah.
Oh.
The browse for the hell of it, try and control that. Hey.
This is A, this is B, A is pointing to B, and we're removing that. B can point to several things. Each of those things can point to several other things, they can point to each other, and so on.
Hold the mic up.
The descendants of B are going to be everything that you can get to from B by doing employee name dot length dot, the add method, dot the documentation for the add method, dot the length of the documentation, which is going to be a lot of properties. And in fact, you can have infinitely many there. But we're using the mark and sweep, so we're not going to have an infinite loop, but we are going to get to all of them. This is going to be an external variable. Call it C. A, B. This is D. And C and D are going to also refer to these objects. We want to find out, by the way, these are all going to have arrows in the actual implementation. C and D are still going to be variables in the program that still exist, that the program refers to, and that and the objects which they point to are still going to be reachable from the program, which means you're going to be able to still reach this one and this one, but not all these, depending on which way we drew the arrows, and not this one, which means we have to collect these, but not these. And make sure we do that reliably. The way that we're doing that is starting with the count field of the extra data fields that every object has, which are just used for the reference or for garbage collection alone. I think we figured out at one point that you can compress those extra fields, the extra information, into 32 bits. If you limit the number of references that there can be to an object to 2 to the 28th, because you only need 4 bits for the extra mark and sweep information. So I mean, that's not going to take a lot of extra space, but it still is an extra word for for the reference counting. The count of B, or the count of these is going to be equal to the total reference count. The count that we're computing of these is going to be less than the reference count because C and D still have references, and we didn't reach C and D when we were looking at the descendants of B. In this example, the reference count here is going to be 2, the reference count is going to be 3, and the count field, or the garbage count, you could probably call it, is going to be 2. Those aren't equal. You're going to have 3 and 2 here again, but these are all going to be 2 and 2. So we know that none of those are going to be reachable. After we've figured that out, excuse me. There's another early exit over here. Skip that for now. We can come back later. We're going to do another sweep. We're going to go through all the descendants of B, which don't include the variables in this example, and don't include the 2 objects that are off to the side that the variables refer to, but do include all the other objects. It's just another mark and sweep. In this case, anything in this case, anything that the two objects that C and D refer to is also going to be reachable from the program. So we want to exclude those, or we don't want to collect those. Like if there was a reference going from right to left, then we'd have to remember not to collect those. Which means anytime we get to an object that's still reachable, we have to go through all the descendants of that object, and even if we've already visited them, go back and mark them as still reachable, even though we thought they might have been not reachable before. But we're going to get through all the descendants of B, so it's still reliable, even though we might have to go through it twice. Also, if we've established that an object is reachable, then there's no way that we'll figure out that later on that it's not reachable. So we're going to have to visit every object twice maximum. It's not like we're going to have to keep going back. So that's why we're using the queued to and the checked to attributes, and they're called to because they occur in stage 2. Just sort of a mnemonic. Yeah, and again, it's just still the mark and sweep. You start off with the original B, which is why we use the inconvenience alias here, because right now it would be inconvenient to have to look at just that one letter. Pop off the object at the front of the queue, or sorry, again at the back of the queue. Go through if it's reachable, if one of the objects that it refers to is reachable, we don't have to do anything. I'm a little distracted, I can't remember why. If it is reachable, or sorry, if the node is reachable and then the object that it refers to is not, that means we visited the object but not the secondary object, then we have to append that. Set that, or mark that as having been queued now, and then also mark it as reachable. If it hasn't been checked, then compare the count and the reference count. I should have called this the garbage count. I couldn't think of a good name for it. Mark that as reachable, and then append that to the search again. And again, this might be the second time that we've put in the queue, but again, it's only twice. Set the checked, set the queued to flag. And lastly, while we're going over all the objects, we're going to clear out the checked 3 field. How are we doing for time, by the way?
We're short on time. 5 minutes.
All right. After that, we're pretty much done. The reachable flag is going to be accurate. That we figured that out, and we're done figuring that out. It's going to be true for all the objects after stage 2. So we just we could use a linked list here. And actually, if we were using a doubly linked list, we could build this during stage 2 as well. Just when we find that something is reachable, again, remove it from the linked list. That's an optimization. Otherwise, another mark and sweep, basically, go down the descendants again and add things to the unreachable queue if we've, in the end we figured out that they're not reachable. Then lastly, for all of those objects which are back in this example, B and the 3 over here, but not these 2. Magnets. For all the unreachable objects, the ones in the lower left over there, remove all the references to all the objects that it points to, and then clear out the object. And we can also call free at this point too. Or we go over the list again and then mark it. Then call free on the objects, which are not referring to anything anymore. This is the drop the references step right here. That's it. The running time complexity, the asymptotic speed of graph algorithms is really bad. So you're going to have to amortize this across multiple successive calls to remove reference. That's the bad news. I didn't analyze the complexity formally. You could probably find it on the Wikipedia page. There's one catch, I guess. If you get to here, you can't check. You can't just say, this is something that I tried to do probably a few times. Figured out I couldn't do it, then thought I could again. Tried to put it back in. You can't check if the reference count of B is 0, because it might be referring to something that also participates in a cycle. That's the only catch. There were the 2 early exits, but otherwise, it's pretty slow, but it gets the job done. You can look at the test suite that I have here. It's somewhat thorough. I wouldn't say it's that great, but it's not completely. It's not totally short. And then there's a random test, which looks like the last time I edited it did 10,000 tests with some structure, which you guys can read on your own.
This is all very interesting. I love graph theory, and I think it's really interesting. But I've never had to collect garbage in Python. What application are you using this in?
This is the way that Python does it. This is pretty close to the Python implementation. Okay. I don't know if Java does it the same way, if Ruby does it the same thing. I think that those are all.
So you're not doing this like, oh, Python can't take care of garbage properly. I'm going to be doing the garbage collection myself. Is there like some application that you're working with that's particularly memory intensive and you have a limited space and you're doing garbage collection manually? Or, I mean, it's very interesting, don't get me wrong. I'm just wondering, like, is there something I'm going to get into where I need to do more manual garbage collection?
I'm only 32, I don't know for sure. Probably not. The way that Python does it, you can get to the guts a little bit with the GC module. You can look at the object or the list of objects that haven't been collected. If you're implementing a Python object in C, there are 2 methods that you want to look at, the TP visit and the TP clear. You might be able to guess what those are. The visit one was the one that iterates over the refs out list that I was looking at here, and then the clear is the one in the last step, which is drop all the references. You can't even do any execution because those might still be in the list of garbage themselves. Some of their references might have been dropped already, but not others. But that's where you get that working in Python. Otherwise, you might. I mean, if you do something more efficiently, but
Yeah.
This is basically what Python does itself. So yeah. Go ahead.
So did you mainly just do this as a way as just like an exercise in theory and a way to familiarize yourself with garbage collection, more than something you can actually use in an application?
Yeah.
Okay.
If you want to write something like this in C, it'll be a lot longer and a lot harder to read, and work on it while you're working on it. So I prototyped it in Python. If you want to take something like this into C, you can start here.
Eventually, you try to port it into C, so you can, I don't know, use it with. I don't know what you can use it with, like your own.
Well, I don't know any objects, because you don't always know when you can call alloc and free, right? Or even delete on an object in C++. You don't always know that. You might have a reference, but you might not, so you use reference counting. But, that has this problem. So, I haven't yet, but, next week, I could get an email, get a job or something, and have to do that.
Quick survey of the room. I've been using Python like 8 years, and I think I've used GC once. I'm wondering if anybody else has used it at all. Is this okay? I'm seeing like 2 hands, 3 hands. Okay, that kind of answers your question.
Right. I mean, I've done like garbage collection in C, but that's, you have to. But not.
There's the del method, the special method name of user-defined objects or user-defined classes. If anyone's ever tried to define the del method, sometimes it won't get called if an object is in a reference cycle.
Even if you call that, it's not necessarily going to release something back. Python garbage collection isn't as good as some other languages because it doesn't always release the memory back.
Not immediately. Sometimes it holds on to it in special lists in the implementation.
I was wondering if there's why there's no tools that'll analyze the code to see if I know some code, the reference counting works really good, and some code drives the GC crazy. And I wonder if there's a source level in that analyzer tool that'll give you some hints on that.
I don't know. I haven't heard of one. Source code tools are really slippery.
Yeah.
Again, I'm only 32. Have you heard of type inferencing?
Yeah.
When you look at the context that a variable or an object is used in and try to figure out what types it could possibly could be at different points, say it's always a list here, it's always an int here, and then figure out that a list is always always and only has integers in it, or floats, or strings or something. You can use optimizations then that way. Again, that's really hard to do. I mean, it's possible, but I don't think there's a lot of cases it's been done. In particular, Python's more problematic for that though, because it has all the dynamic methods, exec and eval and stuff. You can reassign an object, and the compiler won't know about that, at compile time or even at source time.
Is your code available somewhere for us to look at and dissect and steal for reference?
That's what it's for. Yes, it is.
You can post your link to the mailing list.
Yeah, are you on the mailing list? I'll just put my projects page up on that. Yeah, this is my projects page. I mean, this is number 84, I think. There's this one over here. This stuff is all really boring and a little interesting. If you see something on there, I'd love to, come down here and talk more. I'm from the suburbs, so I don't get out here that much.
Thank you.
Yeah. Have a good night, everybody.